Hi everyone, it's my pleasure to meet some of whom I already know and new faces. So this is the new method that we propose to screen for bioaccessible lead in urban soils, and this is still ongoing and research, so welcome your comments, critiques and further suggestions. This research is being done at Brooklyn College in New York, City University of New York, but we also collaborate with Columbia University, who was this original idea, and Francisca is here also. So hopefully we will collaborate together on this and publish the paper, and you will see next time the whole data set together. So why are we doing it? Because lead is a neurotoxin and it's commonly present in urban soils. It has a negative effect on cognitive development of humans, especially children, because they're mostly more sensitive than humans, than adults. And also soil lead is very immobile. It doesn't really move in soils a lot. Usually in the lab we test for total concentrations, but what is really more important is to test for bioavailable concentrations, or the fragments, percentage of contaminants that can be available and uptaken by human body. So the alternative for bioavailability is in vitro measure that is called bioaccessibility, and it's a measure that is performed in the lab, which is considered as the estimation for bioavailability. So how both are done? Metal bioavailability is the key factor in risk assessment and procedures for contaminated sites. Right now, most common way to measure bioavailability is to test on animals, which is called in vivo studies, which is very expensive, time-consuming, unethical, and not practical measurements. So bioaccessibility is the key and the proxy for bioavailability that should be used. In vitro tests also have their negative sides, and it's usually time-consuming. It takes a few days to perform the test. It's not very cheap because you need to get some, ICP-MS running and get some chemicals. So urban soils are extremely heterogeneous, and it's extremely important to have so many tests done on them in various parts of the city, and it can be very pricey to do this kind of in vitro test. That's why we trying to come up with a test that we can use, perform with the XRF, which is very affordable and quick screening test. So XRF has been widely used for solids, soils in our case, and less for liquids, but it's still possible. The ability of X-rays to penetrate matter enables non-destructive, non-contact analysis of solid and liquid samples with a minimal sample preparation, high repeatability, and little operator training. There is some pre-concentration that is required because, as some of you who work with XRF, you know that there is such thing as detection limits, and you need to have at least 10 or 100 ppm of concentration of metal in order for it to be detected. If it's less than that, it's hard to detect. That's why you need ICP-MS. So we need some pre-concentration. The objective of our study is to develop an approach, a new approach for low-cost and rapid assessment of soil lead bioaccessibility that can be conducted in the field using a portable X-ray fluorescence analyzer, and you can see how it looks. We have this is the XRF, which is like a kind of flipped, because this part you put the sample inside of the box, a liquid sample or a solid sample, and there is a computer attached to it, so you can get the data right away. The question that we're trying to answer is that, is the proposed method reliable in terms of reproducibility, stability, matrix effect, and accuracy? And how is the method compared with the results obtained with the standard US protocol, method 1314? This is the first study that explores use for XRF on measuring liquid soil solutions for bioaccessible lead. Of course, there are some studies that try to measure other things, but for bioaccessibility lead is the first time. For our study, we developed a protocol. That's the proposed method, although it's not the only method that we did during our research, and I will tell you after what else we did. So we picked 15 urban garden soils in New York City with various contaminant level, so we can determine detection limit. The lead range from 250 milligram per kilogram up to 500 milligram of lead. We use particle size that is less than 1 millimeter size, something that people, gardeners, or wherever people whoever works in the field, you can easily sieve through sieve in field conditions. If it's smaller than that, it's very hard to sieve it through, especially if it's a little bit moist. We air dry the samples if they were too wet, or to sieve them right away if they were able to go through the sieve. So our simplified acid leaching is 1 to 10 ratio of soil to 0.4 molar glycine solution. We extracted the samples at room temperature for 1 hour. So basically we mixed them really well and left them at room temperature to extract. And EPA is using glycine solution, that's why we used in our test as well. Then we filtered our extractions through syringe filters, and we analyzed an XRF. And this is basically what you get at the end, extracted solution. And the depth should be about, or the volume should be 15 ml in order to have a good reading. And you should also avoid bubbles when you measure an XRF, otherwise it will change the readings. We use some quality controls. We added the spikes with different concentrations of lead as our standard additions. We use Montana 2710A as the standard reference material because it's also used by the EPA protocol. We use duplicate and replicate, and we compared XRF analysis with ICP-MS, which are more reliable, accurate, and precise. So this is the first result. We tested a few different solutions, extraction solutions. We had 1 normal HCl, 0.1 HCl, 0.03 HCl, and then 0.4 glycine. So glycine at pH 1.5, which is usually used in EPA protocol, and HCl is the considered an acid that is close to our stomach acid. So we tried to use different varieties and see what's going on. EPA states that we need to have pH 1.5 solution before the extraction in the range plus like 0.05 or minus. So, and after the extraction, pH should not change and still stay in this range, 1.5 plus minus 0.5. I took 5 different samples and did the analysis extracting them with these different solutions. So we see that the 1 normal HCl is quite acidic, it's way lower than 1.5. The same for 0.1 HCl. Then 0.032 HCl is kind of close to what we get except this sample. And we know this sample has lots of calcium. It has also lots of phosphorus and organic matter, but it does have lots of calcium. This is what brought the pH up. So it tells us this definitely doesn't work. And only glycine solution gave us the right range that we should have after the extraction. So we tested the samples with glycine 1 week apart, the same sample set, in order to see if we have any differences, and we can see there is no statistical difference between 7-day measurements, which tells us if you bring your samples from the field, you don't have time to measure them right away, you can do it at least a week older, but I think it can go even further than that. Just the one problem is that if you use the cups, they may leak, XRF cups, so if you use something else, then you can do it even longer. We also compared our samples with different XRFs, one from Brigham College, another from Columbia University, and there was no statistical difference. We had identical results practically, which means these results are reliable. You can measure them with different analyzers and get good results. Soil matrix effect. We try to evaluate soil matrix effect and see if there are any changes during extraction or after. So we added lead spikes to 2 different samples. So DF sample is a little bit acidic soil, pH 6. It has low phosphorus content. It has lead about 300 ppm or milligram per kilogram and low organic content. SCG soil is quite different. It has more than 2,000 milligram per kilogram of lead. It has total organic content more than 20% and has very high phosphorus as well. And pH was 7.5. It has lots of calcium. So we can see that when we added spikes into the extracted solutions right before we measured with XRF, there was no difference. So the correlation is like 1-to-1, which tells us there is no soil matrix effect, and it can be also a reliable measurement. When we added the same spikes to the same samples, but prior to the extraction, right to the soil, and when we added glycine, mixed it up and left to extract for 1 hour, we saw there was a really huge difference. So, but the difference was for this SCG sample that has lots of phosphorus and organic matter. And you all know that lead binds with phosphorus and organic matter. That's what happens during 1 hour's extraction. It's precipitated or sorbed in the soil. So that's our result. And we tested XRF measurements versus ICP-MS. We took DI water and added the standard additions or spikes with different concentrations of lead and measured on XRF versus ICP-MS. And you can see that how well the points align on the trend. So we can definitely say there's like 15% off deviation with XRF readings compared to ICP-MS. So we have more samples, and we confirm this is the percentage of deviation, and we can just use the correction factor for that and reliably use it further. And the final slide of the result is that, great. This looks like a complicated graph, but it's not. So what we have here is the 3 different methods that we tested. On the y-axis, we have extractable lead using 1 normal nitric acid, which is quite strong acid, can dissolve anything. HCl, 1 normal HCl acid, and then glycine glycine solution at pH 1.5. And the x-axis is extractable lead by EPA protocol. So EPA protocol is the oven dry soil that is sieved through 250 micrometers, and particle size is very small, and it usually shaken on a rotator or shaker for at least an hour at 37 degrees. At 0.4 glycine solution, our proposed method is a pH 1.5. The samples were air dried, sieved through 1 millimeter size, and temperature is room temperature, trying to mimic the conditions you can do in the field to make it easier to work with. And with the acid, samples were also dried, but we didn't sieve them. We just avoided big chunks of rocks or leaves and just used regular soil, unsieved soil. Temperature was also room condition. And we see here that very interesting that nitric acid had the highest correlation with the EPA protocol, and then followed by HCl, which is like 0.8 R squared 0.85 and 88 for nitric acid. Glycine had this still significant correlation, but it was 54% deviation from the EPA protocol. So what was thought about it that maybe the nitric acid is so acidic, so it compensates for all other criteria that we avoid, like sieving through 250 micrometers and not use 37 degrees, and actually we may get much closer correlations by just having more acid extraction solutions. And also, if we do more, if you use glycine, we can get, if you do more samples, here we have only 12 samples, but we, let's say, have 100 samples and we still have 54% of deviation, we can say that we calculate for correction factor and we can still use it because it will be a good model. So the proposed screening method with the glycine solution is can be used with XRF analyzer for rapid, economical, and field applications. So anyone can use it, either you're a gardener or just a scientist who work in the field. You just need to have an XRF. And XRF can be used to measure lead directly in liquid samples. although the readings may be 15% off and higher than expected values. Correction factor can be used if this bias is confirmed to be consistent for a larger number of samples and across different XRF instruments. We did not see any significant matrix effect, but there was precipitation on sorptions when we added spikes into the soil directly. So we still need to do more research to confirm our findings and optimize the specific screening methods. And so it will be more comparable with the EPA standard protocol that are currently being used. Thank you very much for your attention, and thank you to our collaborators who help us with our research. Before I finish, I would like to invite every one of you to our Urban Soil Symposium in New York, which is going to be on November 29th and 30th at New York Botanical Garden, hosted together with the Russian University of People Friendship in Moscow. So you're welcome to come. It will be a great platform for not only scientists, but for practitioners, for governors, for officers, just anyone who is interested in urban soils. Thank you very much.
Questions for us?
Hi, thank you for this talk.
Thank you.
One thing I was wondering about is, to me it seems like basically what you're looking at is XRF versus ICP in solution, like how accurately those line up. But I was wondering then why you were also using a different soil solution ratio. Why you wouldn't just use the EPA 1 to 100 and instead you did 1 to 10 and then try to see how that lined up?
Yeah, that's a good question. So because it's not going to be detected by XRF. If you do 1 to 100, you might get like, I don't know, 1 ppm or 2 ppm, which is not detected by the XRF. XRF can only detect it like 7 ppm and higher. So that's why you have to bring ratio lower to get detection limit for XRF, which also does not allow metals to be extracted in solution if you have less solution, right? 1 to 10 versus 1 to 100. So that's why we had to try other solutions to see what will extract more. Yeah, that's why we try to use acids and glycine to see which one will give us more concentration.
Could you do like a 1 to 100 and then just like heat it up until you
But then it's not going to be a field method anymore.
But if you're shaking it for an hour.
Oh, you just shake it. You just shake it and you leave it for 1 hour. No. You shake it just to mix it.
Okay.
And then you just leave it for 1 hour.
Okay.
And you just hang out in the field. And after 1 hour, you come and text with XRF.
Okay.
Well, if you want to shake it for 1 hour, it will be better. You can actually get more extraction. But I mean, if there might be some field rotators, it will be great.